So Goksel Dedeoglu is a long-standing Embedded Vision Alliance participant and content contributor to the website. Today, he's actually got 2 talks that he's giving, one in each of the tracks. First this one, and then later on this afternoon, one in the other room. This one's on embedded Lucas-Kanade tracking, how it works, how to implement, and how to use it. And his abstract says it's intended for technical audiences interested in learning about the Lucas-Kanade tracker, also known as the Kanade-Lucas-Tomasi tracker. Invented in the early 80s, this method has been widely used to estimate pixel motion between 2 consecutive frames. He's going to present how it works and discusses its advantages and limitations and how to make it more robust. Thank you, Goksel.
Yeah, thank you, Brian. Good afternoon. I'm happy to be back here on stage and to tell you about the Lucas-Kanade tracker. I want to start by acknowledging the contributions of Andrew Miller, who has spent a couple of summers with us at TI. He did lots of algorithm optimization, development, prototyping, and he's now a PhD candidate at the University of Maryland. Before really diving into Lucas-Kanade, I want to sort of take a moment to invite you to think about motion in general. So I think a lot of solutions so far, different tools, applications, have figured out that motion is very rich in information. If you can detect and measure and understand motion in a scene, we can enable lots of different applications. For example, in automotive, we can understand the flow of the scene, and we can understand what the car is doing, and we can also reason out what other vehicles are doing. In video security, we can observe a scene and infer what people are doing, maybe as a crowd behavior, or we can analyze the traffic in a given scene, such as in a retail environment, or such as a road intersection. And for human-device interaction, basically, you already know the famous examples of Kinect and alike that are all based on motion, on gestures. And there are many other applications out there that extract and analyze information about human face expressions, which are all motion-based, and including hands and limbs and other moving parts. So camera, in understanding the motion, has already proven to be a very viable sensor type. It's not the only one, but it's already providing so much information that it begs to be exploited. Now, what the camera is going to see is really a 2D snapshot of the scene. And if you can take multiple snapshots, you have your first chance of understanding the motion of the scene that is surrounding the camera. Now, the task of the computer vision algorithms that look at motion is to understand the motion in the images to infer the motion in the scene, in the 3D world. And as such, some of the applications are going to involve cameras that are moving. Some others are going to be static cameras, but things in the scene are moving. The frame rate is going to be different. The range of motion is going to be very different from application to application. But at the end of the day, these algorithms, such as classifiers, detectors, 3D reconstruction algorithms, are going to need to relate one image to the next to infer the motion that's going in the scene. So the Lucas-Kanade algorithm is a key component that gets typically built in as a building block into many of these applications. There's often confusion, lots of sort of buzzwords being thrown around. I just want to take a moment also to tell you about what kind of tracker Lucas-Kanade is. It's actually, compared to all other trackers you might hear about, see a demo of on YouTube, it's actually a very simple tracker. So for example, I picked 2 dimensions to contrast what other trackers there are out there. One dimension is the temporal support. So is this going to be a frame-based or much longer than a single frame, more like a movie, over days maybe even? And the other axis I picked is the complexity of the model. So what we are going to talk about is not going to have any understanding of something like a human body model or face model or having hypotheses about where things are going, such as different sort of Kalman filter trackers, particle filter trackers, that kind of stuff. It's going to be here on the lower left side. It's going to use 2 frames, and its model is actually the image itself. It's going to use 2 image patches from consecutive frames, and then it's going to infer, it's going to estimate the motion of that local image patch. So it looks like this. You take 2 images, hopefully as close to each other as possible in time. The Lucas-Kanade algorithm runs, and out comes, in areas where you have probed it, flow vectors. If you have probed around the car, you'll get vectors to the left, for example, on the black car. If you have probed around the white car, you'll get vectors in the other direction. This method actually goes back to Bruce Lucas's dissertation with Takeo Kanade back at CMU in 1981. And over the years, it has really proven itself to be a very practical, very successful, and robustly running solution for this. Of course, people have come up with generalizations as well as simplifications. And another paper that was written about what kind of areas are best to track in images is a classic in and of itself, actually. The good features to track by Jambo Shi and Carlo Tomasi was looking at this class of trackers and was saying, okay, what are then the good features, image features that we should latch onto and track? So this is the Lucas-Kanade that I'm going to talk about now. So you are going to have 2 frames, 2 images, and the fundamental assumption underlying the algorithm is that the brightness is not going to change on corresponding points in the 2 images. So the pixel intensities are assumed to be the same from frame t to t plus 1. Mathematically, imagine a 1D function for simplicity. It will be like the f function in blue and the g function in red. All the difference between them is a certain offset. And we are trying to estimate that offset. And of course, this offset, this motion, can be different at every pixel. So we have 2 intensity measurements, image 1 and image 2, for that pixel. And we are trying to estimate the motion vector, which is 2-dimensional, let's say horizontal and vertical. So we don't have enough data, actually, measurements, to solve for the 2 variables that we have. So it's an underdetermined system, a very classical example of a sort of ill-posed problem in computer vision. What we're going to need to do is to bring in more constraints, more information or stronger assumptions about the problem. And the particular way Lucas-Kanade goes about this is that it assumes the motion around that point in a small neighborhood around that point is actually constant. Let's assume it's the same, let's say, vector h that will apply to all those pixels around the point of inquiry. And it will pose this as an energy minimization problem. What if I was looking at the translated version of the first image and looking at the comparison, let's say sum of square differences, and if that was the energy to be minimized, and the correct answer then will come out as the vector h that minimizes this equation. So here's the algorithm flow. The objective function is what I have just shared. The line of attack is going to be a linearization, Taylor expansion of the image that is translated by h. Basically, what we end up here is the h that we are interested in, variable, and here's the image gradient. And this is actually a quadratic equation. You can solve it, and here's the form of it. And because this approximation was really done for the sake of taking a sort of good guess about what the translation might be, the algorithm actually involves iteration over this. So you do basically consecutive, iterative Taylor expansions of the image, and then you solve for the improvement of the displacement. And you repeat this until convergence. In practice, anywhere between 5 and 10 steps, iterations of this seem to, in general, work very well for a large number of points. So So when should we expect this to work well? Well, for one thing, the image regions where we are going to compute this need more or less some texture. Mathematically speaking, we're about to invert this matrix that is components, has the image derivatives in it. If you have a purely blank region of the image, such as the red box here, let's say, I picked the sky region, that's going to be actually very, very ill-conditioned for a matrix inversion. And that's not going to be a sort of ideally sort of strong point where you can do Lucas-Kanade. So image texture typically is sort of the best indicator of a good area you can track. And there are lots of papers, lots of actually dissertations on just that topic. It also works well when the motion is small, because inherently we have done a very local approximation, very local expansion, and we are iteratively trying to get to the better answer. So the closer the data is to our assumptions, the more successful the tracking is going to be. Now, this also begs the question as to, why shouldn't we take more frames? If we sample in time more densely, if you have a higher frame rate, the motion should be smaller, and we should have a better chance of tracking it. That is true, actually, except that means you have a higher frame rate requirement for your computation as well. So in ideal conditions, you'll have the right compute power to do as high frame rate of a tracker as possible to really bring your tracking component to a successful point. And if actually there's always this debate about which compute should go into the cloud versus should stay in the cameras or embedded and implemented on the edge device. Lucas-Kanade is probably a very good example for an algorithm that should reside, best or better closer to the sensor, because you cannot afford that lag between where you are capturing the data and what the algorithm assumptions are. So when the motion is large, though, we are not sort of out of tricks. Multi-resolution approaches, such as image pyramids, are typically used. That means you start at a smaller version of the image, and in a smaller resolution of the image, the same patch is going to cover a larger area, and hopefully you can approximate that larger motion better at that level. And you can refine that solution by moving to the next higher resolution image level. So that's a very common multi-resolution approach that people use in motion estimation, in stereo, and many others. So there are, of course, a lot of parameters to choose from. I picked two to talk about here. One is the neighborhood size, the patch size. What should it be? Should it be 3 by 3 or 11 by 11 or even larger? And also the pyramid levels. Just how many different resolution levels should we care about? Just to give you a sense of what this parameter space looks like, we have explored the different values and plotted the motion vectors here from a ground-truthed data set, the middleware data set. So here's the scene. This actually happens to be a synthetic scene. The ground truth motion is shown in false color at the center top, and that's the motion key. Basically, each color refers to a certain orientation and magnitude of the flow vector. And what we observe is that if you use a very, very local algorithm, very small patch, and just one level of the pyramid, which is the top left of the grid, we get noisy answers. As we increase the patch size, of course, the noise gets lower, except our estimates are a little more blobby. We made a bigger assumption by binning more pixels together. And as we do more pyramid levels, we also get more successful. So there are still no magic numbers to go after here, just sort of very consistent with expectations of how these methods are supposed to help this algorithm. I guess overall, one message is that this is a very graceful degradation. So there's no unexpected jumps or falls in the way the Lucas-Kanade behaves. And the right parameters are going to are going to depend on the exact application requirements. So here's a typical Lucas-Kanade tracking pipeline. As I said, it all starts typically with an image pyramid. So you are going to have multiple resolutions of the image itself, as well as its gradients. And you're going to need a method to decide what features to track. You can decide to track every single point, every single pixel, or you might have a method that gives you a saliency map, and you can track those points. And the Lucas-Kanade tracker is going to take basically these pyramids and these points you want to track, and it's going to produce flow vectors for those points. So the output is going to be literally, per feature, a flow vector, a U component, a horizontal component, and a vertical component. Now, in our work at TI, we actually support Lucas-Kanade tracking by offering a multitude of kernels. We basically have coverage in image pyramids, in gradient pyramids, things like Harris corners, fast orb features for saliency, non-maximum suppression, as well as the actual Lucas-Kanade tracker kernel. And you can implement the full flow with our library kernels that are already optimized on the C6000 DSP. Let me share the sort of specific API, the C function API. The colors are a little off, but doesn't really change the content. In general, our inputs are the images, right? Frame T, T+1, and out we'll get the flow vectors. A couple of aspects that are really specific to an embedded implementation that I want to highlight here. First one is that we are, in addition to the images themselves, the original images, we also get passed into the kernel the gradient images. So we don't compute the gradients inside the kernel because most likely in an implementation, the gradient images are existing somewhere else in the system, in the pipeline. So it's best to give a chance to just bypass that computation if you want to do Lucas-Kanade. The other one is image coordinates, the feature coordinates and the outcome, where each feature was and where they went. And we actually have a fixed point implementation here. So although we do have subpixel resolution and precision, it doesn't mean we need floating point representation. We are using what we call signed 11 bits for the integer part and 4 bits for the subpixel part representation for all these point coordinates. And typical of many other kernels in VLIB, we have a scratch buffer that we provide to this kernel because it has some intermediate variables and representations in there that it needs to keep track of and store in a place. So in a sort of optimal optimization, optimal pipeline, you will DMA your data in and use on-chip buffers with pointers, such as these scratch buffer pointers, to make use of them so that you will minimize the amount of access that you need to do to the external memory. Another word about the fixed point angle there. You might wonder, so fixed point is not just in the feature point coordinates, it's in the entire algorithm. You have seen the matrix inversion there, there's some other stuff going on. You might wonder, how do we know that fixed point is okay for this problem? So we took a close look at it as well. Again, referring to some ground-truthed data sets. This example is from Middlebury. The second column is showing the ground truth motion field. The third column is the floating points, for example, the one you will find in OpenCV implementation. And the fourth column is our fixed point is optimized in VLIB. So this is just one way of looking at the data. This is just one way of convincing ourselves that, yeah, in the ballpark, the algorithm is still behaving the same way. Ultimately, this should come really from your application. So we did not break the algorithm, take undue shortcuts to make this work faster. Little animation there. Okay, let me quickly launch a quick demo video that we have done using the Lucas-Kanade tracker. It's basically just a simple camera-based interface the application we thought of was, okay, what if we have a photo album and we want to be able to navigate through the album by going up, down, left, right to pick the image. And just for the sake of exercising the optical flow field, what if we want to rotate the images as well? So these are the 4 motions for navigation, and then crank left and right to execute the actual image rotation. It's almost arbitrary. This is just one sample application to make use of the optical flow vectors. Before I conclude, I want to say a word or two about what I call quality control for Lucas-Kanade. Now, computer vision, as you have seen this morning, is expanding very, very fast. There's a lot of new resources, new open source libraries that are expanding at a rate that might be actually infeasible to even follow up with. Perhaps an example of that is that in OpenCV, if you dig in, you'll find 2 functions that are labeled Lucas-Kanade. What we have done here is we have taken that data set with the ground truth on the left, and we have evaluated those 2 algorithms. And what we see is that the function called the pyramid-based Lucas-Kanade flow algorithm is giving very reasonable output. So it's a good, faithful implementation. Whereas the other algorithm called optical flow LK is actually far from being a sort of a up to the job. So when you take a closer look, what you find out is that it's a single-step algorithm. So it's not the Lucas-Kanade iterative method. And because of that, it can be up to 100 times faster. But it can only handle very, very small motion. So, and in this particular case, not even sort of able to produce this sort of synthetic flow outputs. And it turns out, in OpenCV, as of today, it's already obsolete. I think this is very interesting to observe because this kind of stuff is very relevant, very pertinent to embedded software developers, embedded architecture developers as well. As you are looking at a new algorithm, some request might have come. You hear about an algorithm, a new application. As you dig in, you might run into implementations that are actually vastly different one from another. And in this case, I think everybody will agree that a 100x difference in performance requirements is actually very significant. And you want to make sure you spec your algorithm and your what you want to show and tell about properly. So it's a communication, really, problem. So to conclude, I have told you about the Lucas-Kanade algorithm. That's at this point a very well understood and widely recognized and deployed algorithm. And we have implemented this on our DaVinci C6 4X Plus DSP architecture. And we have made those kernels available as part of the VLIB Vision library. And the key messages here are that, number one, this algorithm is proven, is well understood. Many people have used it, and they keep using it. So that's good. We know when it works. We know when it has more problems. And the challenge is that it's not easy to compute. It's actually, it can be very challenging for a normal CPU, especially if you want to profile it for an embedded device. And algorithmic extensions are probably going to continue to happen in the next few years too, which means programmability is still key. So what we have found out is that if you have the right programmable processor, if you make the right design trade-offs, such as fixed point, other optimizations, and other parallelizations, it's actually very feasible to arrive at a practical, well-working, robust Lucas-Kanade algorithm on embedded devices. So we hope this will keep to be remain as a useful building block for many applications. And I also included some resources where you can follow up, download some code, look at some data sets, and read about the whole academic world that's actually still publishing on the topic of optical flow. Thank you very much.